Now I would like to introduce my result. CFD analysis of cross-cut heatsink for electronic cooling. As you know, electronic industry has developed rapidly and its power also increased. Therefore, heat dissipation for them is the most important consideration because it can impact their product lifetimes. In this result, we investigate the thermal behavior of real heatsink, which was modeled by inventor 2018, and we imported to Autodesk CFD 2018 to investigate the thermal performance of that heatsink. You can see on the left is the picture of the real heatsink. The right one is the model we created by inventor 2018, and then we import to the Autodesk CFD to investigate to predict its thermal performance of the heatsink. My purpose is to predict the thermal performance of the heatsink by using CFD. After we make the mass calculation, we have total of 138,662 nodes and 534,839 elements. And this is my main result. This is the temperature of the chip. We applied different power on the chip. 1.5 watt, 3 watt, 6 watts, 8 watts, and 10 watts. And we investigate under the different the air velocity. And we can see that air velocity increase, the temperature of chips will reduce. And we can see that if we want to apply the 10 watt chip for that heatsink, the minimum air velocity of 0.25 meters per second. And this temperature of the heatsink of 10 watts with velocity equal 0. This equal 0. You can see with velocity equal 0. This is a natural convection. You can see the hot air will with the low velocity will raise up, and you can see the temperature of the heatsink with the with velocity equal 0. You can see it's very hot. You can see it's very hot. And this is the temperature profile of 10 watts with velocity of 0.45 meters per second. You can see that the heatsink will cooler, and the temperature of chip will reduce. And we investigate the heatsink when we rotate it 90 degrees around the x-axis under the natural convection. And you can see the chart when we compare the zero heatsink and 90 degrees heatsink. You can see that the 90 degree heatsink, the temperature of chip with the heatsink will better than, somewhat better than the 0 degree heatsink. The chip with 90 degree heatsink is average of 1.50 to 2.50 louder than that of 0 degree heatsink. You can see the temperature distribution of 10 watt chip under the 90 degree clockwise heatsink. You can see that with the 90 degree heatsink, the heat is easy to escape to this side. Therefore, it's easy. Therefore, is somewhat lower than the 0 degree heatsink. And we can see the streamline of the 0 angle heatsink and 90 degree angle heatsink. You can see that's the streamline of it. And we investigate the thermal resistance of heatsink. You can see that when we increase the velocity, the thermal resistance will reduce. You know that if the thermal resistance reduces, the chip temperature is low too. Therefore, it's good for our chip. And we investigate the pressure of the heatsink under different air velocity, and we increase the velocity from 0.25 to 0.45. The pressure drop will increase. You know that the pressure drop is depend. You know that if the pressure increase, the fan power will increase too. Therefore, you use a lot of energy. And we increase the velocity, the pressure drop increase, and is proportional to the square of flow rate. Conclusions. In this paper, we study the variable heatsink, which was developed by the Davis 2018, and we simulate it Autodesk CFD. And we some conclusion is drawn as below. The higher velocity will reduce the chip temperature and the thermal resistance of the heatsink. With 10 watt chip, the heatsink will be used with a velocity at least 0.25 meters per second. Or else the chip would be malfunction, damage or lost lifetime. The heatsink can be applied for the chips under 6 watts with natural progression because chip temperature not exceed 70 degrees. Under the 90 degrees vertical angle around the x-axis, the heatsink efficiency is a little bit better than that of 0 degrees heatsink. And the pressure drop of the heatsink is higher with the increase of air velocity and directly proportional to the square of the flow rate. Thank you for listening.